So I will now go on with the second part of this lecture, but before doing that, I will try to recap a bit what I said before. So today we are talking about how to distribute deep learning models on multiple devices and thus scale your model and hopefully speed up your model training. What we have seen is that there are some challenges to it. So this problem known as the increase of the batch size can cause difficulties during training and could cause lack of the generalization capability of the model once deployed. We have seen some of the strategies that can be used to address this problem, and specifically newer optimizers, the way to tune the learning rate, also the warm-up of the learning rate. And this is more related to the way you tune the hyperparameters of your model. So yeah, once again, learning rate, optimizers, and those kinds of things. But there is also a technical aspect of all these distributed training topic, which is very much related to MPI and the topologies that you can implement it with MPI. So yeah, introducing the first part, something about, for example, the parameter server architecture for exchanging the gradients. And now, going on with the frameworks, I will try to go a bit more in depth with Horovod that implements one of these topologies, and specifically the Ringo reduced topology. So I will now switch to my the second slide of this second part, which is kindly taken from Professor Riddle's course on cloud computing, just to so that we are on the same page when we are talking about deep learning. So before I go on with Horovod and the specific frameworks, I just wanted to be sure that you know that there are some libraries that are used in Python to build and then train your models. And among the most widely used are PyTorch, which is not listed here, but also TensorFlow and Keras, and on which I'm a bit more experienced, I have to say. So I will now go to the part related to the frameworks. So in the first part of the lecture, I told you that data parallel, so the approach of distributing the data, subset of the training data between the nodes, is up to now the most widely used approach. And in fact, there are many libraries that enable this. There are actually native libraries already built in the deep learning frameworks. For example, both TensorFlow and PyTorch come with their own way of doing data parallel training. And they do it in a very similar way, I would say, besides the different semantics. Well, syntactics, actually, more correctly. But I've tried to use these to put my hands on these the ways TensorFlow and PyTorch implement data parallel. But I have to say that they are a bit more complicated and definitely less stable than the solutions provided by this other very nice library, that is Horovod. So Horovod is a library that can work on top of many other deep learning libraries, such as Keras, TensorFlow, PyTorch, or if you work in a cloud environment, also Apache MaxNet. And what makes Horovod great is that independently on the underlying framework that you're using for deep learning, Horovod gives you allows you to use just some lines of code, to add just 7 lines of code, they claim, to your existing code to deploy your model in a distributed setting using data parallelism. So a very important thing to remember is that Horovod, but also TensorFlow and PyTorch libraries regarding data parallelism relies heavily on MPI, and if you are training on GPUs, that is very likely also on the Nickel library for exchanging, once again, the parameters. So we will now go on with this slide, where I will try to go a bit more in depth of the algorithm that is used by Horovod to do these sharing and update of the gradients. So before I go into the explanation of this ring or reduce algorithm, I want to recall you what was the problem with the central parameter server. So the problem was, once again, a single point of failure, because you would have one single node that takes care of collecting, averaging, and then sending back the gradients. And also the fact that you are, in a way, overcharging your parameter server if you are in a setting where you want to use a large number of devices for your training. On the other hand, this ring or reduce is very powerful in addressing this issue. So this algorithm works in two steps, in a way. So first step is the share part, the share and reduce part of the gradient, and then there is a second part, which is the sharing of the gradients among each process, so that the model is consistent across the nodes, so as the same parameters, same weights. So let's follow this cycle a little bit. I will just consider one brick of this array, so one subset, one chunk. And you can imagine this as the, for example, the gradient that you want to exchange, but it can be in principle everything you like in this algorithm. So let's follow the life of one of those bricks. So you see, we have three workers, and we want to exchange the gradients that are computed on each model, on each device. So following the life of this first brick, you see that it's just sent with an operation, point-to-point simple operation, to the next worker, and then a reduction is performed. So in this case, for simplicity, it's just a sum, but usually it's an average operation. So you go on. So from worker B, once you have performed this first share reduction, you go on and you send this brick to the third worker C, where you once again perform the reduction step, and you do it again and you send it back to worker A, where once again the reduction step is performed. And you do it for each of the bricks. So we follow just one, but you do it for every brick of that we have. And once you do it, you end up with each worker having one of these bricks that is the global averaged gradient. And each worker will have a different set compared to the others. So now we will have to do this second part, that is the share only step, where you share what you averaged before. So you share the gradients, the local gradients, so that you end up with a global gradient that now, after this second part of sharing only, will be consistent across the models. So each model will share the same parameters across each node. So there is this very nice video that I will not play now for the sake of time, but you can look at it and it will explain you again how this ring or reduce algorithm. But if you want to see why it works better than a parameter server, just let's have a look at this formula. here, so the second point in this slide, and you can see that in a way you get rid, using the Ringo reduce, of the dependency on P. So you see you here divide by P and multiply by P. So what happens is P is the number of processes that you have, so the number of devices, for example, of GPU devices. And that's really powerful because it means that you also distribute the communication part. That is a very crucial point, in the sense that if we waste too much time in communication, then our efficiency during training for sure will go down. Okay, so I introduced one framework, then later on I will talk also about another one that is DeepSpeed, that I only actually use for testing very small models in computer vision. But most of my experience, as I'm a member of the remote sensing lab, is on remote sensing, obviously. So I want to share with you my experience using Orvo, that is the framework that I presented before. And also the reason why it's interesting to research a bit in this field. So as you have seen from practical lecture 10.1 by Dr. Cavallaro, the size of the models is exponentially growing, has been constantly growing over the last years. And also the number of optimizers, the choices, the strategies for training are growing a lot. And so you want, in a way, to speed up all this process of training, and to also to be able to compare while testing your results and find the optimal strategies. But also because once you deploy your model, you want it to be fast in training, but also fast, very important and crucial, in prediction. So an interesting, very interesting topic that is now becoming very popular is called neural architecture research, which on which, by the way, we published, well, our paper was accepted in IGERS 2021 about this topic of finding automatically the best parameters, the best hyperparameters of our model applied to remote sensing. So that's a lot. There's a lot of research going on here, and it's really interesting. But I will today talk about another application of mine, which actually resulted in a journal paper published, but also in a conference paper, also at IGERS 2020 this time, and which is this. So in remote sensing, now from since 2018, I would say, there has been a lot of effort spent to create larger datasets, larger labeled datasets. One of these is called BigEarthNet, and it has been created by a research group at the Technical University of Berlin. And it's very interesting because it poses multiple challenges at the same time. So what are these challenges? So the first one is that it's a big data set. So you have to build a good pipeline to get the input, to put your input into your, to feed your model when you use such large data sets. The fact that it has different spatial resolutions and multiple bands, so it's not a simple RGB problem or grayscale problem of computer vision, but it has 12 spectral bands that have very different spectral characteristics. And also, it's a multi-label problem. So it means, as you can see from the picture here below, that each patch, so each image of this data set, can actually be associated with multiple labels. So not just one, but more than one, most likely, which obviously poses many challenges during training, because it makes it much harder. So the setup that we decided to use was to test this model on the Eureka supercomputer up to 128 GPUs. So we use Eureka before the booster, also the Juva's booster became available to us, featured, I would say, quite older GPUs. In this case, the NVIDIA Key80s that I think are from 2015, maybe. But still, this is a very interesting case because you see that, in a way, using the concept of distributed deep learning, you can make good use also of hardware that is, in a way, also a bit, I would say, outdated by the newer NVIDIA, for example, V100 and now A100 GPUs that are much faster. So you can still speed up a lot your model even using older devices, which is very interesting. Okay, besides that, the model that we use is ResNet 50. That is a classic in computer vision. It's a ConvNet, so convolutional neural network, that what it was new in ResNet 50 was that they introduced this skip connection, as you can see in this figure, to reduce the problem of vanishing gradient, and thus, once again, having a more stable training, which is very important, as I said in previous slides. So, as I said, the challenges were many. So the problems were a big data set, but also multiple bands with different characteristics, and also the fact that we have multiple labels for each patch. So we had to find a good optimizer to do that. And what we did was to use this layer-wise adaptive optimizer that is Lars, that is the one that I presented before in the part 1 of the lecture. We also computed we had to decide which learning rate to use with this formula, depending on the number of GPUs that we were, in each case of our experiments, using. So when we were using a larger amount of GPUs, we scaled also the learning rate, because again, it's very important to speed up the process. Otherwise, it would get stuck into a region. It's very likely that it would get stuck in a region without improving if the learning rate is too low compared to the batch size, the global batch size that you have. And we also used an annealer of the learning rate. So we decreased it after a number of epochs, so that at first, in a way, you capture the general pattern of your data, and then reducing the learning rate, you try to get the into a region of the loss function, which would not be reachable if you use larger learning rate. So we combined these all these techniques also with a warm-up of 5 epochs to scale constantly the warm-up at the beginning. And what we obtained was that we could actually reach good accuracy, so maintain quite good accuracy up to a global batch size of 8K, so 8,000 samples, which, consider the fact that we are in a setting difficult by definition, because we are in a multi-label setting, is, I would say, we were pretty glad that we could do that. I have to say that we were aware of the fact that there were some challenges still open, because one might want to go even beyond this, so to use more than 128 GPUs, for example. Why stopping there? And also, we had a problem with the dataset itself. As I was saying, it's a complex dataset, and the custom-made functions for loading do not work with these remote sensing multiple channel datasets. So we had to implement a custom solution that in the beginning was not very well optimized, I would say. And now it is. So we worked a lot on this, I would say. So after publishing these results on this slide, last year, we're now working a lot on optimizing. We have worked a lot on optimizing the pipeline for the input, integrating very heavy in terms of CPU processing, data augmentation, and also integrating a caching and a prefetching of the data, so that in a way we can load our data iteratively while the GPUs are computing the gradients, so are computing the backpropagation, performing the backpropagation, which speeds up a lot the training and also increases efficiency a lot, which is very important, since what we wanted to do was to take advantage of the newly available NVIDIA A100 GPUs that are hosted on the Jewels booster. And we are now trying to work on this. I want to mention also that in the meanwhile, since there is a lot of research, also new optimizers are becoming available. Two of them are, for example, LAMB, which is similar to Lars, but it's even more adaptive, and Novograd. And also newer convnets that are becoming popular. So ResNet 50 now has been around for 6 years, and a new model that is now a bit, I would say, replacing it is called EfficientNet, which, as you can see from the figure here on the right, is using much less parameters than the ResNets. If you compare, for example, the model B0 to a ResNet 50, you can see that the amount of the size of the parameters is completely different, and still getting a better accuracy than you could before with much larger ResNets models. So how this is done, these researchers, there is a very nice paper that I linked here, this reference, they found a way to optimize the width, the depth, and also the input resolution of the model in a way that you reduce the number of parameters, as you can see, if you follow this curve of the EfficientNets, and also at the same time increase accuracy, which is very interesting. So I want to say that on this we are spending a lot of time and working to improve what we had. And also, once again, on neural architecture research, that I was mentioning at the first slide, in the second slide of this second part, because, as you can imagine, there are so many parameters, hyperparameters that you could tune, that if you did it manually, it would become overwhelming. So a lot of research now is going into that direction, as I said, and also one of our papers at Tigers this year is on this concept, that we try to exploit to optimize faster our models. But that was about my research, which was also a bit the objective of this lecture, to show you also how to use these. And from now on, the last 15 or 20 minutes, I will talk about something different. So in the slides before, I used, as I said, Horovod, which is a very powerful data distributed algorithm. But the frontier of technology is moving fast. The pace is very high, and things are changing quickly. Okay, so in 2020, well, almost 1 year ago, Microsoft released their own framework for distributing training. So while Horovod could actually implement only data parallelism, DeepSpeed not only does that, but can also distribute the model itself. So in a way that is very friendly to the user. I mean, till now you could, in principle, distribute your model, but it was very difficult for scientists to do so. So you had to manually tweak the parameters, manually distribute, send each layer to each GPU. And now these new frameworks by Microsoft does that very efficiently by itself. So Unfortunately, deep speed does not work with all existing frameworks, but has to rely on PyTorch. So that's also, I would say, the reason why I've not tested it thoroughly, because most of my code is TensorFlow based. But in principle, actually, I have also to say that TensorFlow 2, which is the new version of TensorFlow, is becoming so similar to PyTorch, and also using the Keras API, top-level API, that it doesn't take so much of an effort, and things are becoming much easier to transition between one and the other library for deep learning. I have to be honest with you. So again, just to recap this slide, deep speed means that now it's possible to do data parallelism in many different ways. So both data and model. Deep speed comes with some bundled features. Here, it's an optimizer. It's called a zero optimizer, not in the sense of optimizer during backpropagation, but optimizer rather in the sense of making the model more efficient. How taking advantage of the fact that in the nodes you typically have the GPUs, but also the CPUs. So leveraging this fact that you have both, you try to use them for different tasks. So what it means is that actually optimizing the flow of information between these, it becomes possible to train much larger models than it was before possible. So to give you an idea, models, a model with more than a model like Resonance 50 with using 12 channels as we do with a batch size of 500 is already at the limit on an NVIDIA NV100, which is, I mean, a new, well, relatively new GPU and good GPU. So imagine what would happen with models that have billions of parameters, like the new ones, GPT, for example. A second feature that is really interesting is the fact that deep speed comes with an already implemented algorithm for taking advantage of sparse attention with many different masks for attention. So without entering too much in the detail, attention is a bit the new thing in deep learning. So in the 2010s and so on, there was the revolution of convolutions. And now sparse attention is becoming increasingly used. Specifically, if you look at the literature, in the models called transformers, that are also beginning to be used in our field, well, in the field of computer vision, and maybe slowly, let's see, in our field of remote sensing. But deep speed comes with an optimization for that is really powerful, and also comes with its own way of tweaking a modified version of Adam, I would say, which in this sense is a real optimizer. So not like the zero optimizer that was related to CPU, GPU operations and memory, rather than the real backpropagation and the computation of the update of the weights. So in this sense, what they did is to implement a lighter version of Adam that speeds up, well, reduces a lot the volume of communication that is needed between the layers of the model during training. So speeding up the process itself. And yeah, I would say that that was it related to about deep speed. And now I have 3 last slides, which are a bit of my conclusions on, and here I'd like to recap a bit what I've said. And specifically, I'd like to make you understand why these frameworks and why this distributed deep learning is interesting for us. So again, it's interesting for us because big models, so many parameters, and big data sets means that the training time is usually very high. So what it means is that if we can take advantage of the fact that we can now access a large number of devices, of GPUs, we can also speed up a lot our training, just so to recall a bit why we want to do that. Here I have a use case that is the GPT-3 transformer presented by OpenAI last year. That is an extremely huge model that Gabriele already showed, has shown you in page 23 of his presentation. So you would see here how long it would take to train this very big model on a single V100 NVIDIA GPU. And you can easily, well, it has been computed that it would take 355 years, which is a lot. I mean, nobody can wait that long, probably, maybe, who knows? Yeah, but I can't. I can't live so long. So here you should understand, okay, so it makes sense to use distributed deep learning. And in fact, it's used a lot in industry and research. And then I want also to talk a bit about the costs of training this. So, and this concept is related also to the fact that why HPC, why are you taking this HPC course, and why it makes sense to use HPC infrastructures if you compare it to the flexibility that is provided by the services of cloud computing that you can easily find, for example, Amazon AWS. So the fact is that if you compute the amount of money, how much it would cost to train this transformer on the cloud, for example, here there is an example of AWS, Amazon service, you'd see that even in the most optimistic scenario of using the plans with savings and those kind of things, you would still end up with millions for training, which is, I mean, I don't have in my pocket. But also for a smaller application like the ResNet 50 I showed you, also there, it's very, for scientists, it's very important to have access to HPC infrastructures that you can take advantage of, because I tried to compute it by myself, and on the cloud, what I did, so testing and then deploying and then trying again, because sometimes you make some error, and then validating your results, would mean that you train your models for a very long for a very long time. And in my case of this application that I presented you, this paper of IGRAS 2020, it would have meant spending something around 3 to 4 or maybe more thousands of euros, which is a lot. So in this, I think that it's very important to have these figures that are between science and also HPC, that are available also at the supercomputing center, the Jülich Supercomputing Center, because I think that it's very important also for scientists outside of these kind of centers to have access in a more easy way to this very powerful infrastructure that HPC offers us. And in fact, I will also briefly talk about a team that is doing this in Jülich in my last slide. I want also to mention, before I conclude, that Horovod, DeepSpeed are not the only one around the world doing that. Here there are two other frameworks, German frameworks, that are developed in different research centers. So above we have the HEAT, Helmholtz Analytics Toolkit, that among the other features also comes with a very nice support for data parallelism at the moment, but they would like also to extend it to model parallelism with PyTorch support. And also another one, so which is, excuse my Italian accent, but this is Tarantella, which is another framework that promises to do something similar. So yeah, I would say that now your question might be, does it make sense? Well, how can I decide my the way to go? How can I decide the framework to use? And we come to my last slide to recap a bit what I said also about these newer frameworks. There is a takeaway that I like for you to remember that is, in my opinion, is very important. So as I already said, the frontier of technology is moving very, very fast. So in a way, if you are at the frontier, you can lose track of it. You know, after, I mean, you may start you may think that you start with a framework and then it becomes outdated very soon. But in my experience, it's true that the frontier is very fast-paced. But on the other hand, solutions that are successful, like Horovod, tend to become month after month and release after release and version after version, very stable, and so can provide also more support. So if I had to suggest to somebody what decision to take, I'd say that it depends a lot on what you want to do. So if you are most likely somebody who wants to have a stable solution, I would definitely still suggest to use frameworks that are well established instead of using newer things with a much less support. But that's just my humble opinion as a person who is working in this, has been working in this field for only 2 years now. And there is a last thing that I want to comment again between the relationship between cloud and HPC, which is also, spoil you that, question that Professor Riedel likes a lot in his cloud computing course, if you take it. And the fact is that the two things, so HPC and cloud computing, are becoming much more intertwined than they were. Also, for example, think about the TPUs that are offered. So this device is offered by Google. But also a very interesting case study that I like is this new hardware that is provided by Samba Nova, which is a startup, a unicorn from California, that not only provides these racks with these RDUs, they call them, so these new, very optimized GPUs in the end. Not only they do that, but they also provide an interface to use their hardware and to wrap around existing frameworks, they claim. And that's very interesting because it's this trend of offering data flow as a service could be revolutionary in the field of machine learning, where models are becoming so big that a scientist in a university, how can he afford to train these? I mean, also in terms of time to train these kind of models, it would become, they would be put off the market, I'd say, too soon. And in my opinion, this is a very interesting point that we will have to follow in next years and see how it evolves. Regarding that, at the Supercomputing Center in Jülich, there is a team that does that tries to help people who come from outside the field of HPC to deploy and implement and deploy their solution to HPC, for example, with distributed deep learning, and it's the Helmholtz AI consultant at JSC. And there are some members who are scientists and other are software engineers, and they try to provide help to external people who want to deploy their models, their machine learning models on a larger scale. And the very interesting thing is that now, as a final remark that I want to say, is that they are trying to also test and benchmark these algorithms that we have developed, also on the Samba Nova hardware and software that is provided by them. So we will see if all that is claimed by these new companies is true and interesting also for us. So I'll say thank you very much for the attention. I hope you enjoy the lecture, and yeah, that's it. And yeah, just a final thing. Have a look at the bibliography, at the references if you like, because there are some very interesting papers around.